Assalamualaikum dan very good morning pada semua. Hope you can hear me loud and clear.
Waalaikumsalam. Betul Doktor?
Boleh boleh dengar. Right.
Boleh.
Yesterday ada someone message, I think Ketua Kelana, okay. Sama ada if we had class yesterday, but because it was a public holiday in Johor, in JB, in Johor semalam, yesterday. So I forgot to mention that class was cancelled. Okay. So cuma I had a class juga yesterday. It was a IDP 1 briefing. Okay, it's just a short briefing about 1 hour. So tak apalah, yang itu saya go ahead. Tapi for the class, kita punya RC2 class yesterday, sorry for not informing earlier that the class had to be cancelled because of the royal punya birthday. Sultan of Johor punya birthday yesterday. Jadi Johor was we had a public holiday yesterday. Anyway, today kita continue with our staircase design. Okay. In our last meeting, perjumpaan yang the last perjumpaan, we had I think everyone had a general idea of how kita tackle staircase design. Okay, in principle, how we go about to design a staircase. Okay, among the few important points that you need to always bear in mind when you're tackling staircase design is, pertama sekali, to identify supports for the staircase. Okay, from any sketches given, okay, daripada sketches ataupun cross section view ataupun even plan view. Okay, if there is any plan view, sketches dan sebagainya, try to understand from the sketch itself how the staircase is being supported. Okay, and that in principle will determine whether the staircase can be considered sebagai a continuous staircase ataupun a simply supported staircase. Bear in mind juga, supports, beam supporting staircase, okay, usually beams are indicated as penyokong ataupun support for the staircases. Okay, but there are cases where it can be another staircase supporting secondary staircase, a main staircase, tangga utama, supporting ataupun menyokong secondary staircase. So there can be cases where not only beams to act as support, but sometimes in certain cases there can a staircase can support another staircase. Sama konsep macam if you recall balik during your RC1, kita ada rasuk utama ataupun primary beam supporting secondary beam. Okay, so we have a case where beams can support another beam, the main beams ataupun the primary beams supporting a secondary beam. So the same principle can be applied untuk tangga. There can be cases where primary staircases ataupun tangga-tangga utama supporting secondary staircases, okay, menyokong tangga yang kedua. We'll come to that later on nantilah. Tapi just bear in mind before you attempt any soalan ataupun problems related to staircases, very important to be clear on the support for the staircases. Macam mana? How is the staircase being supported? Is it being supported by beams sahaja ataupun is it being supported by another staircase? Does it define the staircase to be a continuous staircase ataupun a simply supported staircase? Ataupun even a cantilever staircase. Ada juga. It can be a cantilever staircase. Alright, so today kita akan continue and we'll look at the first example. Okay, so if any of you ada soalan apa-apa, just interrupt saya saja, or you can just raise your hand. Dalam ni dalam Zoom ni if you feel like you want to tanya apa-apa, you just raise up your hand and then saya stop sekejap lah, ya. Ataupun you just interrupt saya saja. Sir, I have a question. Then I'll stop and we'll listen to what your question is. Okay. Right. So kita continue with the example. We had a look at this schematic in our first meeting that was on Monday last Monday. Okay. So today kita akan continue with the example. Okay. The notes that you have, you can go through the notes. For example, macam this is the design procedure, okay, the step by step punya solution dan sebagainya. Okay. Alright. As we go along kita punya example, it will cover all the items listed here. Right. So the first example is a staircase, given for a staircase. Okay. And from the schematic shown di sini, there are several information that we can extract. Okay. Pertama sekali, again, it clearly shows that there is a beam supporting this staircase, and the beam is located di sini. Okay. This is the beam. This is the beam supporting the staircase di sini, dan juga di sini. These are the two beams supporting the staircase. Once we have identified the support for the staircase, then automatically the position of the support defines kita punya span, which means that once I have determined, okay, this is clearly indicated as a beam supporting the staircase, maka from here I would clearly see that this would be kita punya the span of the staircase for this particular problem. Okay. So if this is the span, which is from center to center, okay, from center to center, this defines the span for the staircase. Okay, defines the span for the staircase. And once we have defined the span of the staircase between the centers of these two supports, then we notice that on the right hand side di sini, okay, on the right hand side of this support, and on the left hand side of the support yang ditunjukkan di sini, there is continuity. Okay, ada kesinambungan. There is a purpose why it is sketched out to be a sort of a continuous ataupun extension of the staircase beyond the support at both the left hand side dengan right hand side ni. If we look closely, it shows there is a continuation to the right from the right hand support and to the left at the left hand support. So this clearly again gives an indication that we are trying to design a staircase where we can model this staircase sebagai a continuous beam. Okay. A continuous beam. I use a black color di sini. Okay. This is my model. Okay. The beam with supports clearly indicated di sini. We have one support over here, and we have another support di sini, somewhere here. Okay. So this clearly indicates that there are two supports for the staircase, which has been modeled sebagai a beam. And satu lagi is that again we look at this portion ni. Okay, there is continuity on the right hand side dan juga continuity on the left hand side, which means to say we are now tackling a problem, a staircase problem, which can be classified sebagai a continuous staircase. And the reason being is that there is continuity on the right hand side beyond support, right hand support, dan juga continuity beyond the left hand support, indicating that this is a continuous staircase. So these are the points that we can pick up, okay, daripada the sketch given, and clearly from here we can safely say that the bending moment to be used for this particular staircase would be of a continuous punya bending moment. continuous beam bending moment, where we will have negative bending moments over both support, left hand support dan juga right hand support. Okay, so from the sketch given, a lot of information can be extracted. Pertama sekali, we have identified the support, mana dia kedudukan penyokong. The position and the location of the support has been identified. Number two, we have identified center to center of the support to be the main span of the beam. Of the staircase. Okay. That is number two. Once we have identified the support, naturally from the center support kepada center support would be defined sebagai our span for the staircase. Number three, there is continuity on the right hand support di sini, beyond the right hand support, and there is continuity beyond the left hand support. Again, this would indicate that the staircase is a continuous staircase because beyond the support there is still continuity, ada kesinambungan. Okay, keselanjaran, bukan kesinambungan, keselanjaran. Okay, kesinambungan ni macam sinetron ni kan. Keselanjaran. Okay. Continuity on the right and left hand support, clearly indicating that the staircase is a continuous staircase as indicated in this schematic idealized structure, which is our beam, and it happens to be a continuous beam. There is continuity to the left of this support and continuity to the right hand side of the support, indicating that this staircase is a continuous staircase, tapi we're looking at internal span of a continuous beam, rentang dalaman rasuk selanjar. Okay. Internal span of a continuous beam. Continuous beam ni ada dua. Satu internal span, rentang dalaman. Satu lagi end span ataupun rentang hujung, still considered sebagai continuous. Okay. Right. So this gives an indication of the solution, the direction of the solution we are heading. Pertama sekali, the staircase can be idealized sebagai a continuous beam. Continuity on the right and left hand support clearly indicated dalam schematic, and we would be expecting that the bending moment diagram for any continuous beam pun, we would have a negative bending moment over both the supports sebelah kiri dengan sebelah kanan, and definitely between the two supports we would have a positive bending moment. So this would indicate a negative bending moment, a positive bending moment, and a negative bending moment. And this would dictate how we provide kita punya reinforcement. Meaning that if this is our negative bending moment, clearly we would need a top reinforcement sebelah kiri, top reinforcement sebelah kanan, over the supports, okay, over the supports, and bottom reinforcement between the two supports. Antara dua penyokong tu we would need a bottom reinforcement. Okay, so seolah-olah macam between A dengan B ni, between the support we will need bottom reinforcement. Okay, sebelah between at the support sebelah kanan ni we would need top reinforcement, as if macam inilah, tapi bukanlah macam ni. Nanti kita akan tengoklah. Okay, and over sebelah sini we would need top reinforcement pada penyokong. So this top reinforcement over support, top reinforcement over support on the right hand side, and bottom reinforcement between A dengan B ataupun between these two supports. So this is the orang kata the rangka solution. Nak kata apa? Framework of the solution going ahead. Even though we haven't used belum lagi tekan calculator, but naturally this is the direction of the solution. This would be the flow of the solution. Okay, and then comes later on baru kita tengoklah, barulah kita evaluate what will be the loading. Loading saya lupa tunjuk di sini. Okay, there would be clearly loading di sini. Okay, pada this beam coming from the staircase. Okay, so all of this is the framework of the solution ataupun rangka penyelesaian. Okay? It's just a framework. Even if dalam test you before attempting a question, okay, you put all of this without the values pun tak apa. So I know that you're going in the right direction. So kalau tak cukup masa pun, you still have marks for your apa nama understanding for the solution for the staircase. Okay, right. So moving on daripada sini, I'll try to save this. Okay, and clear all drawings. Okay, pertama sekali the G and R and G values are given. These two values are given. Kemudian there is a value given here 1.0 pertaining to permanent action. So this would relate kepada our GK. Okay. Tapi in bracket it says excluding self-weight, which means that this 1.0 represents more or less the finishes punya loading, kemasan, pembebanan dari kemasan, loading from finishes, because it is excluding the self-weight of the staircase. So the self-weight of the staircase has to be calculated dan added kepada the permanent action. The finishes. So GK ni, whenever we are doing RC structure, okay, sama ada beam, slab, column, whatever, okay, the GK will always comprise of basically dua component. Okay. One is the main one would be the self-weight component, and the secondary, the primary would be the self-weight component. Secondary component would be the finishes. These are the two most basic load characteristic related kepada permanent action ataupun GK. So dalam soalan, what is given di sini 1.0 is actually the value related to finishes sahaja, because it clearly indicates, it states dalam sini excluding self-weight. So this value of self-weight ni has to be calculated. We need to evaluate what is this self-weight component, and then finally kita add up these two components to have our total GK. So the total GK will always comprise of two components, which is the self-weight component, the main component, and the secondary component would be the finishes component. If we are doing slab design pun sama, if we are doing beam design pun sama. Of course beam tu finishes dia taklah taklah nampak macam slab ataupun staircase. In beams, the finishes can be replaced by brick wall. Contohnya, there is a brick wall on top of the beam. So the total GK on the beam would comprise of the self-weight of the beam plus the brick wall, which is acting directly on top of the beam. So that the finishes punya component can be replaced by brick wall component if you are tackling problems related kepada beam. Tapi if problems related kepada slab and also staircases, then the self-weight and the finishes would be the primary and secondary component of a GK. Now, there is another value QK given in the question. Now, this QK represents dia punya ni lah, our variable action ataupun variable loading. Cuma, sometimes QK untuk staircases is not comprehensive. Maksud saya, if we look at our Eurocode punya loading table, we have QK untuk sekolah, schools, we have QKs for offices, we have QK untuk hospital, we have QK untuk katakan congregation, masjid dan sebagainya. We have QK untuk retail, shopping, dan sebagainya. Different QKs for different condition of the building. If the building is a school building, the QK would normally be around 3.0 kilonewton per square meter. Okay, kilonewton per square meter, QK. Tapi nak tengok, if we were to look for a specific staircase for school, ataupun staircases for hospital, staircases for libraries, tak ada. There is no specific QK for staircases untuk bangunan-bangunan. So what we do is, let's say the building there is a school building, where the QK is 3.0 kilonewton per square meter. This is given dalam code. Okay, it is recommended by the code that we use 3.0 as our live load ataupun QK for schools. When we come to staircases, okay, we would imagine that the staircase would be a very important component kalau berlaku emergencies. Okay? When there is an emergency where everybody needs to use the staircase at the same time. Pada masa yang sama, everyone is going towards the staircase, using the staircase at the same time. So QK untuk sekolah, contohlah, QK for schools, for staircases, we could use a value which is higher than 3.0 kilonewton per square meter. Maybe kita guna 3.5, maybe even 4.0. Okay, so that is how we justify our loading. So if anyone queries ataupun tanya, if another engineer tanya, looking at your design, why have you chosen QK 4.0 for your staircase, whereas QK for normal classroom is only 3.0, but for your staircases you have chosen 4.0, and then you can justify the reason why staircases is slightly higher than the normal loading into slabs for that particular school is because we would expect in emergencies, all the occupants of the building would be using the staircases at the same time, and this would be an indication of the extreme where the load we have increased from the normal 3.0 kepada 4.0 to cater for the extreme loading that might occur when everyone is using the staircase at the same time. That is how kita justify our loading. We can use 3.5 ataupun paling kurang lah, at least equivalent to the loading on the slab. The slab is 3.0, maka staircase pun 3.0. And that is the baseline lah, minimum dia. Okay, try to use something bigger, 3.5 at least, ataupun to be more confident, okay, guna 4.0 kilonewton. So this is how we justify the application of QK untuk staircases, because there is no specific QK for staircases dalam Eurocode. Mana-mana code pun tak ada, because it makes sense lah kalau the building is retail, ni mana retail ataupun office, where office loading is about 2.5 kilonewton per square meter, then the staircases should cater at least sama 2.5 ataupun lebih 3.0, 3.5. Okay. Looking at the extreme end, if we say that for emergencies everybody will be using the staircase at the same time, maka from 2.5 normal floor slab loading untuk office, but for the staircase in the office building I'm using 3.5 ataupun I'm using 3.0. Okay, and there is always a justification di situ. We justify. If anyone asks, there is a justification why the QK is selected to be a certain value for staircases sahaja. For staircases. Alright. So in this particular case, QK is given 4.0. Okay. Grade of concrete grade is 25, steel grade is 500, density is 25, and cover again given a cover of 25 mm, and the bar diameter is seem to be 8 mm. What is not given initially, this is the basic data that is given. What is not given initially is this value, the H value, which is the thickness for the staircase. It's not given sebenarnya, it's not given. This value of 110 is estimated. We need to estimate suitable thickness. H is the kalau tengok di sini, kalau saya enlargekan dia, okay, we have our R and G di sini, and this is the soffit of the staircase. So our H value is taken yang ini, perpendicular ataupun at right angles to the soffit of the staircase, and this value is taken as 110. Now the question is, how do we arrive at this 110? Macam mana nak estimate thickness of a staircase? And for the same argument, when you were doing your RC1, how do you estimate the thickness of your slab? ataupun thickness of your beam, the size of the beam, thickness of slab, we need to estimate, we need to come up with a certain dimension before kita proceed dengan design. So the same argument is used here. This 110 initially is not given. It is assumed, okay, by the author lah, IR Saleh, that 110 is taken as the thickness of the staircase, measured at the perpendicular to the direction of the inclination of the staircase, right? So to obtain a suitable thickness, 110 is by using what is you've gone through earlier dalam RC1, using our deflection criteria. Remember kita punya deflection criteria dalam RC1, looking at beam ke ataupun slab, what you did earlier was calculate the L over D allowable, the allowable span over depth ratio, compare the allowable dengan L over D actual, the actual L over D. If the L over D allowable is greater than the actual L over D, then it is okay. However, if the actual L over D is greater than the allowable L over D, then it's not okay. Deflection fail. Okay, so that criteria of deflection check is now used sebagai kaedah ataupun teknik to estimate suitable thickness of beams, of slabs, of staircases. Macam mana kita nak buat ialah for estimation purposes sahaja, estimation, okay? To estimate, we are not evaluating the actual L over D, tapi for estimating, E-S-T-I-M-A-T-E, for estimate of suitable thickness, maka kita gunakan L over D 30. So macam mana dapat keluar 30 ni? Okay. Okay, this 30, the value of 30 is taken as a rule of thumb. Rule of thumb ni nak kata apa sebagai panduan, hanya sebagai panduan, just as a guide to obtain suitable thickness. Okay, kita tahu L over D for continuous is approximately 26. Okay, around 26 continuous beam ataupun continuous slabs, around 26, 25, 26 for continuous punya slabs ataupun beam. And the modification factor, kita ada modification factor for tension steel, modification factor for span dan sebagainya, is taken more about 1.1, 1.2. Estimate je lah, anggaran. So 26 times 1.1 ataupun 1.2, siapa ada calculator, might be close to around 30. Okay, even 1.3. So that is how the value of 30 is taken as a guide to obtain an estimate of the thickness. Contohnya di sini, we have a span dia berapa sini? Tak nampak saya. Span dia 2800 kan? 2800. Right. So if I were to put in 2800, 2800, okay, divided by 30, dapatlah nilai D dia. Okay. Dapat berapa ni? 2800 divided by D, divided by 30. Dapatlah D approximately 90 plus, 90 lebih kan? 9 times 3, 27. Ni 2800, 93.
Yeah.
Okay, so okay, 93 mm. This is our D. Remember our cover is approximately anggaran dia about 25 di sini. So kalau saya plus the cover plus 25, dapat berapa sini Azinita? This is my H, overall depth. D plus cover, I'll get my somewhere around that.
118.
118. Okay, 118 mm. Okay, this is, remember, an estimate, anggaran. Okay, the H to be approximately 118, 118. Teruk sangat tulisan saya ni. Tidak. 118. Okay. In terms of selecting dimension untuk RC lah, untuk RC, choose in multiples of 25 mm. Contohnya 175, 200, 225, 250, 275, 300 and so on. 1350, 1475. Semua in multiples of 25. Bermakna it's 50, it's 25, 50, 75. This angka ni. Bermakna from 118 ni, I would then choose my H to be approximately 125. 125. This would be my selected value of thickness for the staircase. So from span, daripada rentang, using this estimate, anggaran ni, okay, using this technique, this estimation technique, okay, estimation technique yang ini, I have come up with a thickness of approximately 125 based on the span of approximately 2800. So this is how kita come up with suitable dimension. Suitable dimension ni maksudnya, kalau saya save dulu, clear. Kalau saya jump, let's say if you are using 110, okay, 110 sini. For this example, we are using 110. Kalau saya jump ke the actual deflection check yang sebenar, the actual yang ini. Okay. What we have found out is that from this solution is that the allowable L over D is 35, whereas the actual L over D is 34.6. Sama lah lebih kurang. Okay. On paper memanglah nampak 34.6 is less than 35. 0.6 dengan 35. 34.6 dengan 35. Pada saya nampak sama, exactly the same. Okay. Kalau boleh, we would want to have L over D actual ni much less than the allowable. There is a gap between allowable dengan actual. Kalau this 81 is obtained by using H110. Bermakna dia punya D dia lebih kurang H minus 110 minus 30. 10, 20, 110 minus 30. Lebih kurang 30 mm. 29. Okay. Kalau if I'm using H125, okay, minus 30, my value of D would be around 95 mm. Betul? My value of D lebih kurang 95. Now if I put 95 di sini, okay, if I'm using 95 di sini, okay, Azmita, berapa dapat? 2800 bahagi 95.
29.5.
29.5 lebih kurang 30 lah. Okay. Now we can see the difference between allowable dengan actual. Allowable 35, actual 30. We have a clear difference between these two values. Nampak jelas, clearly we can see that the actual is much less than the allowable. 30 compared dengan 35. This is obtained by using H125. I'm using H125. So this is what I mean when we are choosing certain dimension. Okay, kita gunakan fallback balik kepada deflection criteria. L over D 30 for staircases, for slab pun sama. But for slab, remember you have LX dengan LY. For each slab ada shorter dimension, ada longer dimension. So L di situ, L over 30 tu, L is referring to LX, the shorter dimension. Bagi D equal to 30. So from there kita dapat thickness, suitable thickness for slabs. Right? So in this case for staircases, kita gunakan L over D 30, maka it seems that 125 is a more workable punya thickness, because from 1 to 5 ni we obtain our actual L over D is only 30 compared to the allowable, which is 35. So this is the reason why proper selection of thickness is very important from the beginning. Before kita start design, we need to estimate suitable thickness, and that suitable thickness can be obtained by using deflection criteria. Okay, and the deflection criteria yang digunakan pada awal-awal tadi is actually an estimate lah, anggaran yang digunakan L over D 30 tu, 30 tu. Untuk beams for normal beams, RC beams, use L over D 15. For slabs dan juga staircases, guna L over D 30. Again, I stress this is for an estimate of suitable thickness sahaja. Just to obtain suitable thickness for staircases dan juga for slabs dan juga for beams, right? So anyway, walau macam mana pun tak apalah, because this this example is using 110, but you can work out baliknya nanti. Okay? You can try and work out and look at the solution if you are using 125. Okay? And you will find out that in the deflection check, it is clearly a more practical solution, because we have an allowable and an actual L over D clearly berbeza, distinctly different. Nampak jelas the L over D actual is much less than the allowable by using 125. Tapi of course on paper, this solution is still acceptable because 34.6 is still considered less than 35. Walaupun kita tahulah 34.6 tu actually 35 lah tu. 35 plus compare dengan 35. So we are at the borderline case. 110 is a borderline case. So anything more than 110 would give a solution where the actual L over D would tend to be lower than the allowable L over D, right? So tak apa. So that is the solution that is with us today. Any questions so far? Ada apa-apa soalan? Anyone?
No, Doctor.
Ada We have about 38. 38. Adalah seorang dua yang tak dapat attend ni. Ke tak bangun pagi lagi. Okay, so as I mentioned earlier, we have our beam di sini. Idealized structure sebagai beam, right? As a beam di sini. And now we need to know, because we have identified this to be a continuous case. Continuous case, okay. Continuous case with support di sini dan support somewhere here. Okay. Now the next stage is to obtain the loading. What would be the loading pada tangga di sini? And this is where we need to evaluate what is our GK and what is our QK. Of course, QK is given di sini. QK can be obtained directly daripada sini. This is our QK. Cuma GK ni, remember there are two components. One component is the finishes, and another component would be the self-weight component. So now we are trying to evaluate what would be the self-weight. And to obtain self-weight, as I mentioned earlier, we have an inclined section, and tapi whatever loadings pada structure will always be in the vertical gravitational punya direction, vertical load. And because the section is inclined, maka we convert the section kepada what is termed sebagai equivalent ataupun average thickness. Staircase tu diubah suai menjadi tebal purata. The staircase is then converted kepada average thickness.